Hello everyone. In this video, we are going to see about the complex reactions. A complex reaction takes place when the reactant are converted into product in multiple steps or more than one step. Or, in other words, it is the reaction whose mechanism comprises more than one elementary step. A major goal in chemical kinetics is to determine the sequence of elementary reactions or the reaction mechanism that comprises the complex reaction. The main important evidence for a composite reaction is the detection of reaction intermediates. And the main difficulty in interpreting the velocity measurements due to several other reactions taking place simultaneously along with the main reaction. So what happens? The smooth progress of the reaction will be disturbed. This is the type of complex reactions. In this case, Sherwood Rowland and Mario Molina won the Nobel Prize in Chemistry in 1995 for proposing the elementary reactions involving chlorine radicals that contribute to the overall reaction of ozone to oxygen in the troposphere. Coming to the types of a complex reaction, there are three different types of complex reactions. The first one is a parallel reaction, second one reversible reaction, and the third one is the consecutive reactions. In this video, primarily we are going to see the kinetics of parallel reactions. We know that it is the parallel reaction is the one in which the substance decomposes or reacts in more than one way. So this parallel reactions, in other terms, it is also called as competing reactions or side reactions. When we see, the reactant is going to be considered as capital A, and the reactant A is going to give you two main products. One is B, the other one is C. So here B is going to be the main product and C is the side product. Let us consider the K1 as the rate constant for the conversion of A to B, and K2 is the rate constant for the conversion of A to C. In the graph, we can see that the concentration versus time, the concentration of the reactant A continuously it is getting decreased because the reactant is converted into a product. Whereas for the concentration of B and C, it is going to be continuously increasing because it is going to convert into a product. Considering the kinetics of the parallel reactions, let us consider the initial amount of the reactant A at time t is equal to 0 is considered as small a. After a particular time, when the reaction is getting converted into product, the amount of reactant A is left unreacted will be considered as A minus X. So, the rate of formation of B, that is the product B from the reactant A, is considered as rate constant into the concentration. That is, the rate constant is K1 into A minus X. Similarly, for the formation of C from A will be K2 into A minus X. After considering the rate constant for individual, we need to consider the overall rate of the reaction. So the overall rate of reaction is always the summation of the two rate constant, that is K1 and K2. So overall rate of the reaction is K1 into A minus X plus K2 into A minus X. In this term, A minus X is going to be the common terms. Therefore, taking it outside, we will get it as dx by dt is equal to K1 plus K2 into A minus X. So, integrating between the limits, t is equal to 0, x is equal to 0, which is going to be the initial, and t is equal to t and x equal to x will be the final. Therefore, when on integration between the limits, taking the concentration terms to one side and the rate constant and time to the other side, we get dx by a minus x is equal to k1 plus k2 into dt. Therefore, we will get it as k is equal to 1 by t ln x by a minus x, where we can say that k1 plus k2 in that equation 2 will be considered as k. So the values of A, that is the concentration of A, can be obtained by computing the concentration of A with time. We should also know the values, that is how much amount of B and C is formed, that is the Z. Z is nothing but the ratio of formation of B to the ratio of formation of C. Therefore, the estimation of amount of B and C at the end of the reaction is given by the value of Z, which is equal to K1 by K2. So, considering the values of K and Z, the values are obtained by experimental measurements. Hence, the values of K1 and K2 values are composed. This is the examples of parallel reactions. The first one is nitration of phenol. We know that phenol on nitration with dilute nitric acid, it gives two products. One is going to be the orthonitrophenol, the other one is a paranitrophenol. The orthonitrophenol is the main product and the paranitrophenol is the side product. The second example is reaction of ethyl alcohol under different conditions. The third one, decomposition of camphor carboxylic acid in alcoholic solution. The last one is the combination of benzene with chlorine. So benzene on halogenation, it gives you two different products. Not only the parallel reaction will come under the composite complex reactions, also we have seen the other two types of reactions. One is a reversible reaction and the other one is a consecutive reaction. A reversible reaction, it is a one in which the product of the chemical change react together to form the original reactants. The reversible reaction do not proceed to completion. The overall rate of the reaction is influenced by both forward and the backward rates, and its progress decreases, ultimately becomes zero at the equilibrium point. This causes serious disturbances in reaction velocity measurements. The last type of composite reaction is a consecutive reaction. It is the one in which the reaction proceeds from reactant to final products through one or more intermediate stages, and the overall reaction is a result of several successive steps. Since many intermediates are found in the reaction, it is difficult to find out the rate of the reaction. So, questions can be asked: what are the complex reactions? Why parallel reactions are also called as complex reactions? What are the ways to find out the rate of a parallel reaction? Thank you.